Good day everyone, I am Dynamic Ansag and today's lesson video is about temperature measurement. Objectives. At the end of this lesson, students are able to identify the types of temperature, understand the temperature. But before we dig this lesson, let's at first test your knowledge to answer this short motivation. Identify if the statement is true or false. I give you 5 seconds to answer. Let's start. Number 1. A thermocouple is type of remote sensing thermometer used to measure the temperature of distant object. Okay, your answer is correct. It's false. Number 2. The optical pyrometer is used for measuring the temperature of the furnace, molten metal, and other overheated materials or liquid. Okay, your answer is correct. It's true. Number 3. A pyrometer is a type of remote sensing thermometer used to measure the temperature of distant objects. Okay, your answer is correct. It's true. Number 4. This type of sensor detects thermometer emitted from the object and measures temperature based on the amount of infrared radiation. Okay, your answer is correct. It's false. The last number. Number 5. The thermocouple is an electrical device consisting of two dissimilar electrical conductors forming an electrical junction. Okay, your answer is correct. It's true. And now, let's start to our lesson. Expansion pressure thermometers. So, there are 3 types of pressure thermometer. First is liquid expansion thermometer, gas expansion thermometer, before of pressure thermometer. First is liquid expansion thermometer or fluid expansion thermometer, field system thermometer, an instrument for temperature measurement compressing a fluid filled bulb connected by a capillary tube to a device that changes shape due to expansion of the fluid caused by a temperature increase. How does liquid thermometers work? Liquid in glass thermometers are based on the principle of thermal expansion of substance. A liquid in a glass tube, called a capillary, expands when heated and contracts when cold. A calibrated scale can then be used to read off the respective temperature that lead to the corresponding thermal expansion. A liquid expansion thermometer works by using the thermal expansion of a liquid with a capillary tube to measure temperature. The precision of this method varies by the liquid used, but all use the fact that when most liquids are heated, they expand. Gas expansion thermometer. Gas expansion thermometers are widely used in heavy industry, on board ships, but also in food production and other sanitary systems. By adding switch contacts, the thermometer can also function as a temperature protection and functional safety system. A cooling water system can be switched on if the thermometer measures temperature either by a grid tube or flexible capillary inserting into a thermowell. The temperature is accurately measured by the gas inside the thermometer expanding and contracting in relation to the temperature. Before or before actuated thermometer. indicates media temperature using a temperature-equated liquid in the sensing elements and a highly accurate, high-quality pressure gauge. As the media temperature increases, the capillary field fluid vaporizes, increasing pressure in the Bourdon tube to activate the movement. In before pressure thermometers, a highly butyllite liquid is used but only partially occupies the thermometer volume. The liquid begins to vaporize and fills the rest of the volume, which thin. As a result, the pressure rises until equilibrium between the liquid phase and the gas phase is reached. Thermocouples. Thermocouples or thermocouple is an electrical device consisting of two dissimilar electrical conductors forming an electrical junction. A thermocouple produces a temperature-dependent voltage as a result of Seebeck effect, and this voltage can be interpreted to measure temperature. So I have a video here. Please watch on how thermocouples work.
Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be looking at the thermocouple to understand how it works as well as some of the different types. This video was sponsored by Danfoss. A typical thermocouple looks something like this. It usually comes with a handheld temperature probe or even a multimeter. They are also built into these solid cases for a much more rugged design. Thermocouples are very quick and easy to use. By simply plugging the probe into the measurement device, in this case a cheap multimeter, and selecting the temperature setting, we can get an accurate temperature reading in no time at all. And this will work for many applications. With a thermocouple, we connect two different metals together at one end, and the other ends connect into a terminal block. Then we use a voltmeter to read the voltage difference between the two. The voltage here will be very, very small. When we connect the thermocouple to a multimeter and then apply heat to the junction, we can see it will generate a voltage. As you can see in this example, we're able to generate a very small voltage using a flame. And once we remove the heat, the voltage diminishes. Thermocouples are available in different temperature ranges. These are shown by a letter which indicates their rated temperature range. The most common type is K. This is a very general purpose version. Each letter uses a different combination of materials. This will give us a different temperature reading and allows different temperature ranges. If we held a metal rod in our hand and place the other end into a flame, we know the rod will heat up and this heat will travel along the length of the rod to our hand. We can see this by using a thermal imaging camera. Notice the thermal energy travels along the length of the copper wire away from the heat source. What's happening here is the heat is exciting the atoms and molecules which form the material structure. The heat causes the molecules and the atoms to vibrate. This vibration is so tiny you would not be able to feel it with your hand. The excited atoms will allow their free electrons to move more easily, and they will move towards the cooler end of the rod. This only occurs because there is a temperature gradient, a difference in temperature from one end to the other. So, at the cooler end, we'll have slightly more electrons than at the hotter end. And as electrons are negatively charged, we therefore get a slightly negative and slightly positive charged ends of the rod. Voltage is like pressure. We're measuring the difference or potential difference between 2 points. If you imagine a pressurized water pipe, we can see the pressure using a pressure gauge. The pressure reading is comparing 2 different points also. The pressure inside the pipe compared to the atmospheric pressure outside the pipe. When the tank is empty, the gauge will read 0 because it has nothing to compare. both are now the same pressure. The same with voltage. We are comparing the difference from one point to another. If we read across a 1.5 volt battery, we get a reading of 1.5 volts. But if we try to measure the same side, we wouldn't read any voltage, because there is no difference. We can only measure the difference between two different points. By the way, we have also covered how a battery works in detail in our previous video. Do check that out, links can be found in the video description down below. Coming back to the thermocouple, if we connected two wires together of the same material, let's say they were both copper, and we then applied heat to their end to create a temperature difference, then the electrons would scatter and build up at the cold ends. However, they would build up in equal amounts in each wire, because they are the same material. So both wires will conduct heat equally and the temperature gradient will be the same. Therefore, our voltmeter wouldn't be able to measure any difference. However, if we connected two wires which were made of different materials, say one was made from copper and the other one was made from iron, then the two metals will conduct heat differently, so the temperature gradient will be different. That means the electron buildup at the cold ends will be different. And so we can connect a voltmeter to this and read a voltage difference. To make this into a useful tool, we just calibrate it by testing the device against known temperatures and marking down the voltages generated. Then we simply use a formula to calculate the temperature from the voltage measured. For this to work best, we should submerge the cold junction into an ice bath. That way we get a voltage with a reference relative to 0 degrees Celsius. Remember I said about the pressure in the pipe and how we are comparing it against the atmospheric pressure outside? That's because we know the pressure outside the pipe is atmospheric pressure. So, for the voltage reading to be accurate, we need to measure against something we know. So we use ice water because we know this temperature is a constant 0 degrees Celsius. This method is used in many science labs. However, as you can probably tell, it isn't very practical for most engineering applications. So instead, to improve the accuracy, we leave the cold connections at equal ambient temperatures, and then we compensate for the difference by measuring the temperature of the connection and applying a formula to offset the error. To measure the temperature of the connection, we often use an RTD temperature sensor, which we'll look at next. RTD stands for Resistance Temperature Detector. This is also a fairly simple design. It's probably easier to understand than the thermocouple. They usually come in these different designs for engineering applications with a rugged casing. How do these work? Well, we know that electricity is the flow of electrons in a circuit. We have covered how electricity works in detail in our previous videos. Do check that out. Links can be found in the video description down below. When we pass electricity through a material, let's say a copper wire, the material will have some resistance to the flow of electrons, and we can measure this resistance with a multimeter. Different materials will have different resistance levels. For example, this 1 meter length of copper wire shows a very low resistance of just 0.2 ohms. But this 1 meter length of nickel chrome wire shows a very high resistance of 22.1 ohms. The temperature of the material will change the resistance of the material. Most conductors will increase in resistance the hotter they get. That's typical of metals. For example, this copper wire shows a resistance of 0.1 ohms at ambient temperature. But when heated with a flame, it increases up to 0.9 ohms. This occurs because as the atoms and the molecules become excited, they're going to move around a lot. So this makes it harder for the free electrons to get through without a collision. Using a formula known as Ohm's law, voltage is equal to current multiplied by resistance, which means that as long as we keep the current the same, a change in resistance will cause a change in voltage. And as temperature changes the resistance of a material, we can measure the voltage to tell the temperature. We use a material such as platinum because it has a near linear resistance versus temperature gradient. We test the material at known temperatures to obtain the graph. For example, at 0 degrees Celsius, the material will have a resistance of 100 ohms, and at 100 degrees Celsius, it has a resistance of 138.5 ohms. There are many different designs for this type, but typically they're either a film type, where the platinum is coated into a ceramic plate into a pattern and sealed in glass, or it will be a platinum wire wound around a ceramic core, again sealed in glass for protection. Okay, that's it for this video, but to continue your learning, then check out one of the videos on screen now and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, Twitter, Instagram, LinkedIn, and of course theengineeringmindset.com.
Radiation thermometer. A type of sensors detects infrared emitted from the objects and measure temperature based on the amount of infrared radiation. Because this is a non-contact type, temperature measurement of moving or rotating objects or objects that may be influenced by the contact of sensor can be achieved. Pyrometer. A pyrometer is a type of remote sensing thermometer used to measure the temperature of distant objects. The word pyrometer was originally coined to denote a device capable of measuring the temperature of an object by its incandescent visible light emitted by a body which is at least red hot. Pyrometer device for measuring relatively high temperatures such are encountered in furnace. Most pyrometers working by measuring radiation from the body whose temperature is to be measured. Radiation device has the advantage of not having to touch the materials being measured. So I have videos here on how the pyrometers work.
The word pyrometer is derived from the Greek word pyro, meaning fire, and meter, meaning to measure. Back in the day, the original pyrometers were non-contacting optical devices which intercepted and evaluated the visible radiation emitted by glowing objects. Since then, the term pyrometer has evolved to mean a non-contact device which measures thermal infrared radiation emitted from an object to determine surface temperature. Simply put, the best example of a pyrometer today would be an infrared thermometer. So what does infrared have to do with temperature? All objects having a higher temperature than absolute zero emit infrared radiation. The higher the surface temperature is, the higher the frequency of that radiation. Infrared thermometers detect the infrared radiation frequency and convert that into a temperature reading. How does an infrared thermometer work? In its most basic form, an infrared thermometer consists of an optical system and a detector. The optical system consists of a lens that focuses the energy emitted from the target object onto the detector, which is sensitive to that radiation. The detector takes that focused radiation from the optical system and converts it into a temperature reading. For example, most IR thermometers use something called a thermopile. A thermopile converts the focused incoming radiation into an electrical signal using a series of tiny thermocouples. The signal is measured and displayed on the screen in the form of a temperature reading. The big advantage to using an infrared thermometer is that you don't have to come in direct contact with the object whose surface temperature you are measuring. However, there are some issues to using an IR thermometer that should be considered, especially in industrial applications, like emissivity. Highly polished metals typically have very low emissivity ratings, since they tend to be very reflective of ambient infrared energy and less effective at emitting their own electromagnetic waves. If you point an infrared thermometer with fixed emissivity at a stainless steel pot filled with boiling water, you might get a reading closer to 100 degrees Fahrenheit than 212 degrees Fahrenheit. That's because shiny metal is better at reflecting the ambient radiation of the room than it is at emitting its own infrared radiation. Some industrial infrared thermometers come with adjustable emissivity settings, so you can more accurately compensate for the type of surface being measured. Also, direct line of sight is required. An infrared thermometer cannot measure accurately through transparent objects such as clear plastic, clear liquids, and most types of glass. You can measure an accurate range of temperature through certain types of glass that fall within the wavelength spectral response range of the IR sensor. So if you aim at an object through a closed window, don't expect to get an accurate reading on that object. While IR thermometers offer a convenient way to measure an object's surface temperature, it is crucial to select the right type of device for your application to ensure accuracy in temperature readings. Still have questions? We have answers. Call or chat online with one of our engineering experts at 𝚘𝚙.com.
4 types of pyrometer: radiation pyrometer, optical pyrometer, digital pyrometer, and infrared pyrometer. First is radiation pyrometer. It's a pyrometer that measures the intensity of radiation from a body having an extremely high temperature. A radiation pyrometer is non-contact temperature sensor that infers the temperature of an object by detecting its thermal radiation emitted naturally. The basic principle of the radiation pyrometer is it measures the object's temperature by sensing the heat or radiation emitted from the object without making contact with the object. It records the temperature level depending upon the intensity of radiation emitted. Optical pyrometer. The optical pyrometer is used for measuring the temperature of the furnace, molten metals, and the other overheated material or liquid. It's not possible to measure the temperature of the highly heated body by the help of the contact type instrument. Optical pyrometer operate within the visible spectrum to measure temperatures typically in the range from 700 Celsius to 4000 Celsius by comparing the photometric brightness of the heated object against the brightness of a standard source, such as an incandescent filament. Digital pyrometer. A pyrometer is a type of remote sensing thermometer used to measure the temperature of distant objects in the molten usage. It is a device that from a distance determines the temperature of a surface from the amount of the thermal radiation it emits, a process known as pyrometry and sometimes radiometry. A digital solid-state thermometers provides an excitation current to the sensor and measures the linear signal from the sensor. Now we have the thermometer conditioning the sensor of its output. The signal voltage or resistance is the analog design. Infrared pyrometer. Infrared pyrometers allowed users to measure temperature in applications where conventional sensors cannot be employed, specifically in cases dealing with moving objects or moving machinery or conveyor belt, or where non-contact measurements are required because of contamination of hazardous reasons, such as high voltage, where distances are too great, or where the temperatures to be measured are too high for thermocouples or other contact sensors. Infrared thermometers or pyrometers measure temperature from a distance. This distance can range between miles or a fraction of an inch. Infrared thermometers are often used in circumstances where other sorts of thermometers are not practical. For example, if the object is very fragile or dangerous to be near, An infrared thermometer is a good way to get temperature from a safe distance. Infrared thermometers work based a phenomenon called black body radiation. Anything of a temperature above absolute zero has molecules inside of it moving around. The higher the temperature, the faster the molecules move. As they move, the molecules emit infrared radiation, a type of electromagnetic radiation below the visible spectrum of light. As they get hotter, they emit more infrared and even start to emit visible light. That is why heated metal can glow red or even white. Infrared thermometers detect and measure this radiation. Infrared lights work like visible light. It can be focused, reflected, on, or absorbed. Infrared thermometers usually use a lens to focus infrared light from one object onto a detector called a thermophile. The thermophile absorbs the infrared radiation and turns it into heat. The more infrared energy, the hotter the thermophile gets. This heat is turned into electricity. The electricity is sent to a detector which uses it to determine the temperature of whatever the thermometer is pointed at. The more electricity, the hotter is the object is. Well, that's all, and thank you.